we can look for the solutions of those questions. And then also for the previous two assignments which I'd sent through, let me know which questions would you like me to attempt from those assignments too. So for the rest of whatever is left, time is left, we will start solving those questions. I wanted to talk today more about cylindrical cavities or cylindrical circular cavities. And basically, previously we had looked at these cavities and I had shown you the simplest possible mode which could be present there. And that mode, previously we basically had seen the mode TM, TM010 mode, which basically meant that there was no variation in phi, and there is no variation in phi, and we're using so basically we're using J0 term, we're using the Bessel function of 0th order, and we are going to its first 0 point. So in radial direction, the first 0 point has to be fixed there, and the last 0 means no variation in Z. So that's the mode we had looked at. It's the simplest mode to conceptually think about and mathematically solve for. However, we have talked many times now that the TM mode actually has higher loss than the TE mode. So for these cavities, the actual practical mode we normally work with is the TE011 mode. 0 again means no change in phi. So the Bessel function of the longitudinal field, which would be HZ field, would have would basically have uh, uh, would have J0 as the term, and the one would be going to the first root of the boundary condition, and the boundary condition for that would be the derivative, and I'll describe this all again later on. The boundary condition would be the derivative. So we are going to the first root of the derivative of the Bessel function of the 0th order, so j prime 0, and we're going to its first root. And then because you know that you have for the TE mode you will have an HZ component present. Because this HZ component is present and this is hitting perpendicularly across the region, uh, there would this HZ component has to be present, so it cannot HZ would be a sign formation, and so it will have to have some variation along the Z direction too. Otherwise, you basically have 0 here and a 0 here, and if everywhere it is 0, then you don't have any mode present. So, so you're basically telling you that you have one wavelength, one half wavelength, which would fit within the Z direction also. This mode actually has the has the lowest loss, and because of that, this has the highest Q, which is present. Last week we had seen the TM010 mode, and we had seen that its Q was roughly 8% higher than a cubic cavity at the same resonance. The TE011 mode, its Q is higher by a factor of 4 or 5 uh, for the same resonance wavelength. So I wanted you to introduce this mode also and do the math. So we need to do slightly more complex maths, but let's do it. I just put it on the slides today so that I can go through them in a decent way. So previously, again, just to remind ourselves, we basically looking for the TM mode. Psi here could mean E or H. And in psi, basically what we go is like we basically have your Bessel function of nth order, and then this nth order would depend upon your upon the value of n, and in z direction uh, you now have a cos function present. So for TM mode, you basically have E electric field in z direction, and electric field in z direction would have to have a cos function present. That electric field is perpendicular to the top and the bottom. So when electric field is perpendicular to a conductor, you get a cos function. And because this cos function is present, you could have m is equal to 0. That term could exist, and thus Tm010 could exist. Similarly, now we want to look for the TE mode. And in the TE mode, we have now Hz present. And therefore, del Hz by del x or del r will have to be 0. So instead of having the function itself go to 0, we have to take the derivative of it, and that has to go to 0. So it's still a Bessel function. The solution is still going to be a Bessel function. It's going to be an h term here. It's going to be a Bessel function. However, the root of the Bessel function has to be such that the derivative goes to 0. So we represent it by saying it's some x prime mn, and basically x prime is basically representing the fact that we are making sure that when we take the derivative of the Bessel function, the derivative of the Bessel function goes to 0 at r is equal to a. And again, you can have sine phi or cos phi terms in it. So this is how the variations happen in the phi direction. Again, whether it's sine or cos doesn't really matter. It's all a shift of the origin where you're calling phi is equal to 0. And because again it's an hz term, it has to have a sign variation in the z direction. All these terms, m and n's, have to be 0. So when we substitute this in the Helmholtz wave equation, this is something we have seen in the waveguides too. But this basically, when we substitute it in the Helmholtz wave equation, you end up getting terms for TE and TM. So this is basically for TM and this is for TE, where K is your propagation constant in a standard material of mu and epsilon. Again, we have seen this many times now. Again, remember this x prime mn is the value of hr. Where do I go? Or value of ha, a being the radius, value of ha, where the derivative of the Bessel function j is 0. What is that value? Where the derivative of the Bessel function is 0. So you have that condition over here. Again, remember what happens is, depending on what happens in the phi direction, you get a specific order of the Bessel function, and it's that specific order of the Bessel function which ends up in the Helmholtz wave equation. So you basically get a term from this term of x prime mn would depend upon phi. So that phi dependence is already accounted for within that term mn, because the choice of the Bessel function, which order of the Bessel function, would depend upon phi. And then you have the confinement in the third direction, and that should be the sum of all the confinements should be equal to k square. Again, these forms are very similar to the forms you have seen for rectangular waveguides. or rectangular resonators, which basically were m pi by a square plus n pi by b square plus p pi by c square is omega square mu epsilon or k square. So the sum of the confinement terms, a square of the confinement terms is equal to k square. But for cylindrical coordinate systems or for Bessel functions, you don't get the phi term, the confinement in the phi direction explicitly out, because depending on that phi, how the variation is happening in phi, the Bessel function is of a specific order. That's how you effectively get that effect. And again, this is the table I have shown you sometimes before too. Uh, and this basically is looking at the roots of the Bessel function and then basically saying if your d by a is equal to what values, where would this lie? So this table is coming directly from Bessel function terms, and it says that like what is the it basically is looking for it's looking for cavity of radius a and length d for different ratios of d and a. So depending upon different ratios of d and a, where would the terms lie? And what it's basically saying is, I'd look at the minimum resonance frequency FR. What is the minimum resonance frequency I have versus the so this is the minimum resonance frequency, which is the minimum resonance frequency of the excited mode, and what is the resonance frequency of that specific mode I'm looking for. Up to d equal to 2 twice a. So for d less than 2a, less than equal to 2a, tm 010 is the dominant mode. For d greater than 2a, actually TE 111 becomes the dominant mode. That basically comes from how the terms of Q show up. For whenever you see infinity, basically means those modes are not supported. So this infinity means mode is not supported. That mode cannot be excited within that kind of a cavity. If you go and you look at the last section when you have infinity over here, if the length of my resonator cavity is infinity, this is basically behaving like a waveguide. And we have already seen that for circular waveguides, your TE11 mode is actually more dominant than the TE101 mode or 011 mode. And again, that is based on the fact because of the derivative. The derivative of the de the derivative of J1 function is has a root which is lower than the derivative of J0 function. The derivative of J1 function is approximately 1.83 or something, 834, I think. So this table basically can tell you which modes are going to be excited at what order. The TM11 and the TE01 modes, these are degenerate modes. These two modes are degenerate. So when TE011 mode exists, TM11 mode also exists for the same frequency. The degenerate mode means that both these solutions, both these shapes are allowed to travel through the waveguide, How we choose which one travels depends upon the excitation. So the TE011 mode, which is the mode which we have said is a mode which is of quite interest to us because this mode actually has the lowest loss in these cavities. This particular mode has the lowest loss. This is never the dominant mode, if you notice. It's always much larger frequency, at least by a factor of nearly 75%. It's the smallest time it could be is for this term over here. It is a much larger uh, cutoff. It has much larger cutoff frequency than the normal mode, than the dominant mode. It's never a dominant mode, but just because how the electric field and how the magnetic field is aligned in this mode, how the magnetic field looks in this mode, the surface current densities actually decrease, and because of that, this mode actually has lowest loss. Again, TE11 mode, it's telling you that you are using J1 function. So you know that the function, the field there is zero field in the center, and the field and the power has been pushed towards the side of the conductor. So that mode actually has a higher loss. And again, if you notice TE211, TE211 is using the Bessel function of second order, which again is pushing the field even further out, and because of that, you have much higher loss. TE011 mode is using the Bessel function of zeroth order, and Bessel function of zeroth order is the only Bessel function where the intensity is peaked in the center. So most of the power is being captured in the center of the waveguide, and because of that, this will have the lowest loss. Again, just a reminder of what the various terms of XMN would be. I've already given you this table. I think I gave you a table up to, I gave you this table up before. I've just added a lot more terms on that table. Mostly for most practical purposes, these terms don't, the higher order terms don't really matter so much. But for mathematical curiosity, it's always good to know them. And again, remember again, we had said this was the dominant mode. This was the time when you got the lowest order. So, uh, with respect to that, now basically, if we were trying to do it, how we can go about solving for this mode. So basically, again, we have said there is another cavity, and why this TE01 mode is very important is that there are times what we do is we have a cavity, and often what we do is we put a plunging conductor which can move around on top of the cavity. So we can move this conductor after some time, like if we move this around, this can basically go over here. So this is basically a movable top wall. Uh, and that what that would do is as you move it around, you are basically changing the mode properties, and because of that, the resonant frequency is going to change. So you can make a tunable resonant frequency tuner by making a structure like that. So I want to generate frequency. One time I want to generate frequency at 2.4 gigahertz. Another time I want to generate frequency at 2.5 gigahertz. All I have to do is just move this wall a little bit. One way to look for these modes is basically assume that yes, we have the electric fields in the R and the phi direction, in the radial and the phi direction. And then because you have a reflection here and a reflection here, I just did this maths to remind you that this is how you basically had looked at in the transmission lines. When you were looking at transmission lines, and you basically had different sections of transmission lines present. There is a wave which is going forward, there is a wave which is going backwards, and this wave has an amplitude variation in transverse direction, which is rho and phi, and the resulting result you're going to get is the beating of those two waves. Now you can solve it this way exactly, or you can solve it the way we had solved before. You get exactly the same answers. Except this is exactly what you had done in the transmission lines too. So we're not really talking anything different here. When we were solving the Helmholtz wave equation directly, we were not really talking anything different than what you had seen in transmission lines before too. And then basically the propagation constant for the TE mode beta Mn basically would depend upon the propagation constant in the medium plus the value of the route you are taking. And for Tm would be the other case. So now basically we have to have the transverse mode to be 0 at z is equal to 0 and uh, and at z is equal to d. So if I was looking at these terms, then this wave and this wave amplitudes, if I force these to be 0, a plus and a minus have to be exactly the same. So otherwise, you do not get perfect cancellation of the two terms at z is equal to 0. So a plus and a minus have to be exactly the same, which is basically saying that these conductors are acting like short circuits with respect to your transmission line analogy. Uh, the value was -1, the reflection coefficient was -1. And then the other thing which has to happen is a plus sine beta md has to be 0 or beta md has to be pi, which is again something we have already seen many times that I have this field in the z direction that I have to fit at least half a lambda in the z direction, which is exactly what this turns out to be. And so basically the frequency components just become the terms which I have. These are the resonant frequencies of these cavities. This is just a repeat of what we had talked about last week. Uh, if if I assume that the dominant mode is TE11 and if I look at the dominant mode which is TM100, so if I look at the TE-NML mode, any arbitrary TE and MNL mode, when we obviously solve for this, Hz is what we solve for, and we said Hz has to have some cos m phi function because you have to fit an integral number of wavelengths in the phi direction, otherwise you don't get to the same point again with the same value. And because Hz is perpendicular to my top and the bottom, Hz is going to have a sign variation, and in the radial component, it is now going to have a Bessel function variation. And since it's Hz value, I know that the derivative of Hz has to go to 0. So I have to look for the derivative terms. What is the place? So x prime m n m is the place where the derivative of j prime n goes to 0. Based on that, we can now use Maxwell's equations to calculate the other terms, and you basically end up getting the other four terms given by these expressions. You basically have for h rho, you basically have derivative of hz with rho. For h phi, you basically have derivative of cos m phi with phi. For E rho, you have derivative of uh, uh, a derivative of the phi relationship with phi, so you get sine m phi, and then derivative of cos with z. So derivative of that with z, you get this sine q pi z term. And for phi term, you need a derivative of this uh, with your x term, with the r term, derivative of the Bessel function with r, and that's it basically. So these are the dominant modes which can be excited. And again, if you were looking for the total energy stored within these cavities, we've already seen that the stored electric and the magnetic energies are equal. So we can just calculate the total electric energy stored and then basically total electrical energy stored and then basically call twice of that. So this twice comes from the fact that WE is equal to WM, and WE we know is half of epsilon of E square dV. dV is from 0 to A on the radial part, 0 to 2 pi to make the phi, and then 0 to D to increase to make the height. And we basically look for the summations of the two terms. Again, this integral, I haven't taught you this integral yet, so just take it from me. Uh, this integral would tend to be exactly this term over here with some constants in the front. So the total energy stored is given by a complex looking expression as shown here. And similarly, we can calculate the power in the conductor loss, which basically depends upon the resistance and upon the tangential component of H fields to any walls, conducting walls, because those create the surface currents over the surface of those walls. So we have H phi field here and Hz fields present. H phi field is, so we have a field in general. We have a field which is turning around H phi. That H phi field is tangential to the components in the so H phi field is turning around that region. It is tangential. It is tangential to the surface around. So you basically go to R is equal to 0. R is equal to A. So that term is the H phi field lying on the surface, outside surface of the conductor. And then you have H phi field at Z is equal to 0, which is over here. And similarly, you have H phi field on the top, but because they are going to be the same, we're just putting two value over there. The Hz field, the field which is along this direction, is only is only tangential to the curved surface. So basically, that's why we are integrating it only over the curved surface. And if H rho field exists, that H rho field which is pointing in the R direction, if that field exists, then it is only tangential to the top and the bottom. So we're just integrating it over here. So in general, for any TE arbitrary N and M mode, we can calculate the Q value to be given by this expression, which is basically substituting the power loss, the power in the cavity divided by the power loss, power loss divided by the power stored in the cavity. If you take a look at different modes which are present within the cavity, uh, these are the solid E fields, and dash is the H field. If I take a look at the mode which is TE11 mode, what you have is the electric fields are circulating in a nearly baseball-like shape. The stitches on a baseball-like shape, and the magnetic field is going from one end to the other end and 90 degrees to the electric field. This is your fundamental, most dominant mode within a waveguide. And similarly, if I go to TM01 mode, then basically what you have is uh, the the electric field is pointing out radially out from the center, and the magnetic field is turning around. That kind of a mode is also seen in that kind of distribution is seen in a TE01 mode, except the things have switched around. The electric field is making circles around, so the electric field is turning around, but now the electric field has max intensity in the center, and as you're going away from that, the value keeps on decreasing. But the magnetic field is radially pointing outwards for that mode. Similarly, you can take a look at other shapes too and convince yourselves what those shapes are going to look like. Uh, so far, we looked at this specific mode and we looked at the Q for that specific mode. Now I wanted to look at this specific mode over here too. And you should be able to see that because in this particular mode, the energy is traveling mainly in the center. The loss of this mode should be lower than the loss of TE11. So alpha TE01 is less than alpha TE11. However, the cutoff frequency for TE01 is higher than the cutoff frequency for TE11. For a circular waveguide, this mode is actually the fifth order mode, which is present from the point of view of circular waveguides. So that is what these distributions would look like in the transverse direction, radial and phi direction. If I now look at the cavity and see what the distribution would look like in the cavity, these are the distributions for different TM modes. And the TM010 mode, we had seen that the electric field is, so if I took a cut of the electric field and I plotted it, the electric field was maximum in the center, according to the Bessel function. It was maximum in the center, and as you went away from the center, the electric, at the radial point, it went to zero. But this zero is telling you that there is no variation happening in the z direction. That there is absolutely no variation happening in the z direction. So the field is uniform in the z direction. Similarly, if I go to TM110 mode, this is telling you that I am going to the first function of the Bessel, first part of the Bessel function, first order Bessel function of order 1, and I'm going to its first zero, but the first term starts from 0 in the center, so it goes to the outside and then I'm just going to the 0, and similarly, if I take a cut, it will be 0 on the other side. So that's what you're basically seeing here. You're basically seeing the effect of that Bessel function. Right in the center, there is nothing happening. As you go further away, things are changing around. And this 0 is telling you that nothing is changing in the z direction. So the value remains the same within the z direction. Similarly, you can now look at other modes. Let's say if I take a look at TM012 mode, it's now basically telling you in the x and y direction, in the r and phi direction, or x and y direction, the distribution looks the same. It's a 0-1 distribution. So in this direction, the distribution looks the same. But what it is saying is in z direction, I have two wavelengths, two lambda by 2s fitting in z direction. And that basically is what you have here. So you have one wavelength here, so one half wavelength here, you have a quarter wavelength here, and you have a quarter wavelength here. So the total, you have two half wavelengths fitting within that region. And again, remember, this is the electric field distribution you're going to see there. If I go to TM013 mode, I'll have three different lambda by 2s present. So you have one half here, another half here, you have one quarter here, and another quarter here, the total being 3. So these are how the distributions would look like in the TM mode. But let's specifically look for this mode TE011, which is an important mode. So basically I'm going to the 0th order. So Bessel function is J0 Bessel function. I'm going to the first root, but because I have to go to the first root in H, I'm going to the first root of derivative of J0. And that derivative, that root is given at 3.832. And then I have one variation in Z direction. I have one lambda by 2 fitting in Z direction. So I have sine pi Z by 2. With respect to that, only H rho and E phi terms exist. And H rho is the derivative of H rho would depend upon the derivative of Hz with its own direction. So derivative, so it will be dependent upon the derivative of Hz with rho direction. And basically the derivative of J naught term is J1. I'd shown you that last week, or I had given it to you last week. So, and then it's the derivative of this with z direction. E phi is the derivative of j with with rho direction. So you basically end up getting these terms over here. If I plot these terms, this is how the field looks like. If I was looking at the electric field is going to be going around in a circle. Its maximum at the center. You remember, the electric field is is in the center, and then it's going around, but it's circulating around. It's turning around within the cavity, and H field is turning around in the Z direction, as it is shown here. So think of it as rings going around in E direction, in rho and phi direction, and H field is now a ring which is perpendicular to these rings and are radially arranged in in the Z phi direction. So electric field lines form closed circular loops centered around the cylindrical axis, and then they are basically threaded with closed loops of magnetic field lines in radial planes. Again, if you notice, there is no perpendicular direction of electric field. There's no direction of electric field which is hitting the wall plates perpendicularly. So there's no surface charges which appear on any cavity walls. There's nothing which is hitting the cavity walls at 90 degrees. So there's no surface charge which would be present there. However, there would be surface current present, which would basically create. So basically, right here, you have H field which is parallel to the boundary, and thus you will create a surface current which will go around that region. But again, notice it's only over small regions where H is perfectly parallel to the boundary. H is looping around in the circle too. So it's only very, very small regions where H is parallel to the boundary, whereas in other regions H is pulled away from the boundary, or the component which is parallel to the boundary becomes smaller. And because of that, you can appreciate the fact that the loss should be the lowest. The surface current which is generated here is the lowest of any modes, and because of that, the loss should be lowest. Again, you can calculate functions of J, and I'll just give it to you. I'll send you these files. You can take a look at it. Uh, but and again, remember the surface currents in this are entirely circumferential. Basically, the surface current is also going around the circumference, and it's maximum in the center. And as you're going further up, its intensity decreases because H field is curving away from it. So what happens now is if end of this cavity is mounted on micrometers on stage, and I can move the change the length, the TE mode can still be fully supported since the current flow is not going to be interrupted. There is no surface current. There is no surface current flowing between this and this. There is absolutely no surface current flowing between the flat part and uh, the vertical and the circular part, the circumferential part. So that means I can put the top conductor separate from the side walls. I don't need to be connected in the side walls, and I can move that conductor up and down, and I would not create any breakage of the current path, and thus the TE001 mode can still be fully supported. This is what allows us to make these frequency tuners, to be able to tune the different frequencies we have. Uh, in the TM modes, there is going to be current flowing from the top surface to the side surface. So I can't have the top surface not in electrical contact. Otherwise, that current is not basically supported, and then your Maxwell's equations basically say, hey, I would not allow this mode to be supported. So that's the advantage of this mode. Movable construction does support it suppresses the other modes. So when I have this movable construction, TM11 mode uh, has the same cutoff frequency as TE011 mode. It has exactly the same cutoff frequency. However, when I have the movable term, this mode is not really supported. The current is interrupted. Current interrupted means that the magnetic field is distorted, the loss becomes quite high, and this has very low, very, very low Q. Similarly, if I was looking at TE11 mode, these currents would be interrupted by the space between the movable end and the side walls. That TE11 mode is also not allowed because of that. In the case of rectangular cavity resonator, the resonator frequency of TE mode basically can be calculated by using this term, where X01 is from the table. And similarly, you can calculate the resonant free space wavelength of the cavity, and in general, you can calculate it for any other mode you want. If we now use the expression for the TE mode and put the value of x01 as 3.832, that's where you get that, at that value you get a 0 for that mode, for that shape. You basically end up getting Q which looks something like this. So if I was making my design to operate at 10 gigahertz and I was looking at the Q values, if you don't, and I just choose D is equal to 2A, then just for copper, just assuming copper here, you find that the Q value is roughly 30, close to 31,000. 31,000. Previously, when we had looked at the TM011 board for similar design, the value was close to 11. So 11,000. So this value has increased a lot compared to the Q we had for TM101 board. TE01 TE011 board has the highest Q of any specific waveguide of any mode. So normally because of this highest Q and because of the fact that this is not interrupted, there is no current flowing from the top to the side, uh, we use this mode for most practical applications. And to excite this mode is also very interesting way to excite this mode. So what you have is you have a waveguide. You basically have a waveguide over here. This is basically a rectangular waveguide. Think of it like a rectangular waveguide. And then you have your cylindrical term cavity which is attached to that waveguide on one side. And what we are trying to do, again, remember in the cylindrical cavity, effectively, when we were looking at it, if I was drawing it this way, you know that you have a J surface current going this way. This was the induced J surface current due to the magnetic field. So now if I'm thinking of, okay, I want to excite this mode, how can I excite that mode? These things are, well, if I have a magnetic field which creates a specific current, then if I can create a current, it will create a specific magnetic field. These are, these go well together. So think of it now. If I can create in this waveguide, so this is how it is attached. If I can create this waveguide such that there is a current Js flowing this way, there is a current Js flowing in that direction, then what would happen is that that current, when I have connected this cavity, there is nothing for it to go forward. That current will have to turn around and will have to go around this way. And if it's going around that way means it is going to excite the TE101 mode, 011 mode because that's what the current it likes. The current going this way is can be easily excited by using a TE10 mode in the rectangular waveguide. So we can excite the TE10 mode in the rectangular waveguide, which basically has electric field in a direction, uh, uh, electric field in the direction that way, which now starts to, and the magnetic field, which is uh, parallel to the conducting boundary, which would allow for the current to be created, a surface current to be created in the JS direction. So basically, mostly we excite these circular cavities by coupling from a mode in a rectangular TE101 mode in a rectangular waveguide. Right, that's I wanted to talk to you about it. It was not part of your curricula per se, but I just wanted to give you this insight into what really happens when we are looking at different what real practical mode we are looking for. So for most of the designs, for most of the applications, when we are doing it, we actually go for TE011 mode. It has the highest Q. It is not the most dominant mode. It is a mode which is actually it's the fifth order mode for these cavities, and however, it has the highest Q because it has the because it has the lowest loss, and because of that, uh, and it's also very easy to excite. And not only is it easy to excite, it is because there's no current flowing from the top to the sides. You can actually make a tunable frequency resonator by moving one of the conductor up or down if we use the specific mode. Do you have any questions on this? Hello?
We are able to hear you, sir. No problem in hearing.
Okay. Oops. Sorry, just a second. I'm just making some slides to write more. But now I wanted to connect these topics to some other things you see as electrical engineers or electronics engineers. And really maths them, but I'll show you things which happen, and then we can start talking about some dielectric waveguides. Just a second. So, so far what we have seen is that if I have two conductors or more than two conductors, if I have a confinement in one direction or any other direction, and then because I have the Maxwell's equations, the wave equation, which is given as omega mu square epsilon E is equal to 0, and we basically had said this was in the transverse direction plus omega square mu epsilon minus beta square E is equal to 0. We end up getting solutions which are discretized. We get solutions which are discretized, and basically what has to happen is that the solution has to be of the form where the electric field has to go to 0. So only very specific values of E can happen. Specific shapes of E are supported. And not only that, each of these shapes has a very specific beta to it. The value of the propagation constant becomes different for each of these specific shapes. Well, there is, as electrical engineers, you're also going to see another effect, and maybe you have seen it, or maybe you're going to take into a course very, very quickly, very soon, hopefully, and that is your quantum mechanics effects. In quantum mechanics, one of the first problems you're going to solve is that I have a infinite potential well. So think of it as voltage V is equal to 0 here, and over here in this well V has gone to infinity. So I've created a potential difference across a region. And the solution you're looking for there is going to be a solution of time independent Schrodinger wave equation. You're going to be looking for solutions of time independent Schrodinger wave equation, which is basically h square, some constant h square by 2m, h square being Planck's constant, del square psi plus v minus e psi is equal to 0. And psi is basically called a probability distribution function. Well, if you look at this equation and you look at the equation we have looked at, the Helmholtz wave equation, these two equations are exactly of the same form. Mathematically, what is this? This is just some constant. I can move it around. I can bring this as 2m by h square. I have a second order I have a Laplacian of psi. I have a Laplacian of electric field. I have some constant here, omega square mu epsilon. This is a constant of material. V is again a constant of potential. Some potential I've added from outside. Beta is the value that solution is going to take, the eigenvalue of the solution. E is going to be the eigenvalue of this particular solution psi. And then you can basically tell me very quickly, hey, if you understand this concept of Helmholtz wave equation, if I am getting discretized solutions with Helmholtz wave equation where the electric field has to go to 0 at the conducting boundaries, well, at V is equal to infinity, when V is equal to infinity, nothing should happen there. So the psi should be 0 here, psi should be 0 here. When at V is equal to infinity, nothing should be able to penetrate into that. So psi should be 0 there, psi should be on the two edges. And then you can easily tell me is, well, the solution is going to take discretized values. You are going to get value of E1, which is going to be a sinusoid like that. Then you're going to get a value of E2, which is going to be have a wave function. The psi is called a wave function. Have a wave function that way, and then there would be a value of E3, which would be something like that. So only discretized solutions are going to be present. E is the energy. So basically, if I have if I try to put some particle in a quantum well, so this is called particle in a quantum well, and normally the idea is to put electron in a quantum well. If I try to put an electron in this quantum well, the electron can only go into energy E1, or it can go to energy E2, or it can go to energy E3. And the probability that it goes to energy E1 would be dependent upon psi 1. The probability that it goes to E2 would be dependent on psi 2. And the probability that it goes to E3 would be dependent upon psi 3. So there can only be some discretized solutions present there too. And thus, these are called quantum levels. And thinking about it, this is behaving like an atom. In atom, you have very specific conduction bands present or valence bands present. Very specific orbits. Very specific orbits present. And those orbits, now if you think about an atom, if you have multiple atoms together, atoms have electrons flowing around them. Because of the electrons, there is a potential which is created. This starts to behave like a potential well. So if I was plotting the potential difference on the atom, it's going to start behaving like a potential well. And because of that, there are going to be very discretized energy levels which are going to be present for the electrons. And thus, and those are, and each, and that electron, the, as you go to a high, each energy level of that electron presence is going to have a very specific shape associated with it. That's exactly the orbits you have seen in your high school. So the orbits are again coming from the fact that you get these discretization of the solutions which are present. These quantum wells you're going to see again in your photonics course when you do optical communication. When you look at semiconductor lasers, these quantum wells play a very important role in semiconductor lasers. It's because of these quantum wells that semiconductor lasers become as efficient as they have become today. And what happens in the semiconductor lasers is you make a quantum bell in the conduction band. So think of it as a conduction band, and then you have a valence band on the bottom. And because of this confinement, so in the conduction band you have basically you have low V here and then you have high V here. Because of this confinement, you will get only discretized values present. And normally you design it so that only one of the discretized value is present, which basically is you want the conduction band to be single mode. Again, the conditions we derived for single mode would be applicable here. And similarly, you have uh, energy levels in the holes. Now, when you pumping electrons in, if you pump electrons, electrons are going to fall down. Electrons try to go to the lowest energy level. Electrons are going to fall down and electrons are going to start collecting here. And when you're pumping holes from the other side, the holes are like balloons. The holes like to go up. The holes are going to start collecting here. And again, when the electrons see the holes, they want to recombine. So when they recombine, when they fall down and they recombine, then you emit light. I won't describe this whole through, but look forward to this. Semiconductor lasers have completely changed the way the world works today. Look forward towards this as in photonics, and you realize that what you're doing in those quantum well designs is exactly what you're doing in these waveguide designs too. The exact same phenomena is happening there also. If you look at the Helmholtz wave equation and you look at the Schrodinger wave equation which you're solving there, Schrodinger wave equation is a solution for the probability distribution of an electron. If you look at the Schrodinger wave equation, those two equations are exactly the same. So all the discussions we did for the waveguides are going to be exactly applicable. The terms are going to change around. But everything else, the way we have discretized solutions, if you choose a specific dimension, you can only have one discretized solution allowed, single mode. If I choose a specific width of the quantum dot or a quantum well, then only a single solution would be allowed there too. Only a single energy level would be allowed there also. So we can play. So everything we have done here would be directly applicable when you take courses in either in solid state physics or in quantum mechanics or when you do photonics and lasers. Remember again, quantum mechanics, the maths becomes the understanding of quantum mechanics becomes really horrible. I don't think anybody really understands fully what quantum mechanics is. So you are left bewildered many times what is happening. But if you make the analogy with the waveguides, at least the maths part of it and the understanding of the mathematical solutions would be very trivial. So I just wanted to correct you with that case. Also, we won't look for those solutions, but uh, so far what we have done. But I'll show you what those solutions would look like without really looking at the solutions, without doing the maths. So far, we have used conductors as the guiding mediums, as the guiding boundaries. So you basically have a conductor here, and you have a conductor which is separated by some distance a, and this is some mu epsilon. And the conductor is forcing the electric field to go to zero here and forcing the electric field to go to zero here. However, these conductors become very lossy at high frequencies. You know that the sigma of the conductor keeps on decreasing as you go to higher and higher frequency. So the conductors become very, very lossy at high frequencies, especially in the optical domain, even in the terahertz too. So the terahertz domain, where you're operating at a frequency of about 1 terahertz, which is roughly 100 microns, 100 to 300 micron wavelength, anything above 100 micron wavelength, or anything below 100 micron wavelength, the conductors become very, very lossy. So we cannot really use these waveguides in the optical domain. We can't use these waveguides when we are trying to send light through them. And that's something you naturally know. If I shine light onto a conductor, the conductor will become really hot. It'll absorb all that light and it'll start becoming really hot. That's something you have observed in your probably observed in your daily lives. So we have another waveguide which is called a dielectric waveguide. And this is something again you will, if you're doing the photonics course, you will definitely have to do it there because this becomes the building block for any photonic devices. A dielectric waveguide in its simplest form consists of a material of epsilon 1 surrounded by epsilon 2. And this is the simplest form. This is called a dielectric asymmetric slab waveguide. And the condition is that epsilon 1 is greater than epsilon 2. That the permittivity of the inside material is greater than epsilon 2. So you have to think of it, you have a material here surrounded by another material, and normally that material could be air, or the epsilon 2 material could be air. But in general, the condition is epsilon 1 has to be greater than epsilon 2. Think of a thin glass sheet in air. Would this guide light? Would this guide electromagnetic wave through it? Now the issue which becomes is, well, Helmholtz wave equation is still true. If I take this waveguide, let's assume it's d apart, epsilon 2, epsilon 1, epsilon 2. And let's assume that I'm just going to take the center at, let's just call this x direction. And this is what I'm going to call x is 0 because it's a symmetric around that point. Life is easy to call x is equal to 0 there. Helmholtz wave equation is still true, but the Helmholtz wave equation here is going to be del square E plus omega square mu naught epsilon 1. It's the epsilon 1 term which is going to be here. E is 0. And the Helmholtz wave equation on the bottom side is going to be del square E plus omega square mu naught epsilon 2 E is going to be 0. The difference now becomes, you can solve this problem. The difference now becomes there are solutions present here, there are solutions present here, there are solutions present in region 1, there are solutions present in region 2, and solutions present in region 3. In a metal waveguide, as soon as you hit the metal, the electric field had to go to 0. And let's assume that the electric field is in y direction and it's propagating in z. So in this case, well, there is no reason that the electric field has to go to 0 here. So there must be electric field existing, and then there is a place where the electric field is existing below too. So now what we are looking for, is there a solution which is present which can solve this problem? And you say yes, there is a solution present. It's a Helmholtz wave equation. It's a second order differential equation. There are two types of solutions for second order differential equation. There is a sine and a cosine solution, and there is an exponential solution. So now what you would say is, okay, I have a cosine solution. If it was a conductor, I would have gone something like that. If it is a conductor, if it was conductor, but now it's not a conductor, so the solution is going to be, it's not going to go fully to 0. The solution is going to be only going to some value on the outside. That would be the sign. I'm still looking for that guiding solution. But another solution which can be present for a Helmholtz wave equation is going to be your exponentially decaying solution. So because I'm looking for the guided part, it has to decay exponentially on the outside. So here the solution would be of the form of E minus alpha x. Here it will be of the form of some A sine kxx, kx being some constant, plus B cos kxx. And similarly here it will be of the form of E minus alpha x. This solution is still going to have, so this could be one mode, the other mode could be now the second order term, so it could be things, it could be the second order term goes like that, and then it decays outside. What you would notice is that the beta of this solution is always going to be between omega square root of mu naught uh, up, omega square root of mu naught epsilon 2. It's going to be smaller than sorry, it's going to be smaller than omega square root of mu naught epsilon 1, and it is going to be greater than mu naught epsilon 2. Or if I was plotting the VP is going to be smaller than 1 by square root of mu naught epsilon 1, but it's going to be, uh, sorry, 1 by epsilon 2. It's going to be smaller than that, but it's going to be greater than mu naught epsilon 1. And that solution is going to travel with a very specific terms. So yes, when you have a dielectric waveguide, you can still support a guided mode even though you don't have a hard boundary condition like a conductor. And the more confinement you get is by having epsilon 1 more different than epsilon 2. Uh, so this is something you would definitely, when you are doing any photonics course, and when you start doing semiconductor lasers or you do optical fibers, the same thing happens in an optical fiber too. You can have an optical fiber where you basically have a cylinder in the center, which is epsilon 1, and then you have a cylinder on the outside, which is epsilon 2, such that epsilon 1 is greater than epsilon 2. And then what you will basically get is a J function inside the Jn kx k rho function inside, and you will get the Hankel functions outside, is which was the third Bessel functions of the third kind, which is the Hankel function, which is represented by k. You'll get that function uh, outside. This is the Bessel order of third, or Bessel function of third order. And again, you'll notice that this optical fiber will have a solution. The fundamental solution would be that the mode is in the center and then is decaying out like that. And then there would be other order modes too. And you'll notice that the answer would be, there would be something called, that the value of that, what there would be a term in there, that value would have to be less than 2.405, the first root of the Bessel function. So when you look at these, when you go to study photonics courses, I believe you do have a photonics course in your curriculum in the fourth year. You would be solving, instead of doing metal waveguides where you force the electric field to go to zero, you would be using dielectric waveguides at that point. And these dielectric waveguides would also support solutions, but the field will not go to zero at the edge. The field would actually penetrate out into the outside. All right, let's stop here for today. This was just to try to get you connected to your future courses. Uh, let's stop here now. And then what we would like to do tomorrow is please go through the questions. Attempt to solve the questions which you think are difficult, and bring me a list of questions tomorrow. If you think are difficult, then you can solve them here. Any questions?